In fold cross-validation, divide the data into several roughly equal parts. Hold out one fold, fit the model on all remaining folds, and calculate prediction error on the held-out observations. Repeat until every fold has served as validation once, then average the fold errors. Each observation is evaluated by a model that did not train on it. The resulting average is therefore an out-of-sample estimate that uses the available data efficiently. 5 or 10 folds are common because they balance computation, bias, and variability. Leave one out cross-validation takes the number of folds all the way to the sample size, so each model trains on nearly every observation. It has low bias but can be computationally expensive and surprisingly variable. With modern software, 10-fold cross-validation is often a sensible default. The purpose is not ritual, it is to compare candidate models on the same out-of-sample basis. The R code begins the workflow by reading the apartment data and fixing the random seed. It samples roughly 80% of the row indices for training and assigns the remainder to the test set. The important object is not the punctuation, but the separation. The test rows are set aside before any model choice. Reproducibility matters here because another random split can produce a different comparison, especially in a modest sample. Next, fit the least squares model on the training frame only. Predict once for the training observations and once for the untouched test observations, then average the squared residuals in each group. The test error should usually exceed the training error because the model was optimized on the latter. If the gap is large, suspect overfitting. The code also makes a useful audit trail. The same fitted object generates both sets of predictions, so the only difference is the data supplied. For cross-validation in R, this page creates 5-fold labels after fixing the seed. Every row receives exactly one label, and an empty vector is prepared to store one validation error per fold. Notice that the folds are defined before the loop begins. We want every candidate specification to face the same partitions, otherwise differences in estimated performance would partly reflect different random splits, rather than the models themselves. The loop implements the algorithm directly. For each fold, the code trains on rows outside that fold, predicts for the held-out rows, and stores their mean-squared error. Averaging the stored values produces the cross-validated estimate. The line excluding the current fold is the crucial safeguard against leakage. Once this structure is correct, we can place different formulas inside the loop and compare their cross-validated errors on equal terms. The Python setup uses the same logic. After loading the apartment data, it defines the predictor matrix and outcome vector, then constructs a shuffled 5-fold splitter with a fixed random state. Shuffling is appropriate here because the observations are not ordered in time. The splitter records which rows will train and validate in each round. A later page will loop over those indices, so the statistical design is visible before any estimator is fitted. The Python loop receives training and validation indices from the splitter. It fits a linear model only on the training rows, predicts the held-out outcomes, records the mean-squared error, and finally averages across folds. The software offers a one-line cross-validation score as well, but this explicit loop is pedagogically valuable. It shows exactly where the separation occurs. Whenever you build a more complex pipeline, every data-dependent step must also be fitted inside that training portion.